You know what time it is. It's Leetcode time. 797 all paths from source to target. So we have a graph here as shown below. And one interesting property of this graph is that it's a DAG. So we're not gonna have an infinite loop, right? So one doesn't point at zero back. So we all have like a one direction edge. So we have 0 to 1, 0 to 2, and 1 and 2 pointing to 3. We're given a graph list that has these this info. So from index 0, we're saying, okay, 0 points to 1 and 2. Index 1 is pointing to 3, and 3 doesn't point to anything. So we're given a target. Okay, our target is n minus 1, so the last element. And we're trying to see, okay, what elements reach there. So 0, so if we're trying to point to 4, we're trying to say, okay, 0 can go to 1 to 4. Okay, 0 can go to 1, then 2, then 3, then 4. Right, so on and so forth. So one thing is we can see that 0 is included in all of these because we need to start from the first node. There will be no self loops. All elements are unique. So the input is guaranteed to be a DAG, so we don't have to care about like infinite loops. So one intuitive way of going about this is to sort of go loop through all of the elements in the graph and see where they point to, right? And if we reach the last number, that means that we reached it, so we can copy that path and add it to a list so that we can do that for output. And we would do this recursively because if we go into the zeroth, if we start from 0, then we need to check 4, 3, 1 because 0 reaches 4, 3, and 1. So for example, we go to 4, so we'll start with 0, 1, 2, 3, 4. So we don't have to do that. We reach 4 automatically. So it's 0, 4, we add that. But then we check the third index, so we go here. So from here, we need to loop through wherever its neighbors are. So this would be a recursive thing, and this would be sort of like a depth first search, right? We're going to go through all of the elements that this node can visit. So let's say that we can create a function called DFS, and maybe that function can take in what node we're starting from, and then the path that we're seeing so far. So how would we do this? So if I were to throw in a function, right, I would do something like, okay, DFS is gonna have a path because we need to see that. We're also going to need to know what index we're starting from. And I think that's good enough because we have the graph here. We know which we're going through. So let's say, and let's have a result list too. Okay, so let's say, because we're going to put in the temporary path to result. So if we have DFS as a function, we're gonna take in the index and a path, okay? And we need two things here, right? We need a base case, like when are we gonna terminate the function, right? When are we gonna pop out? And when we reach the index, right? When we reach n minus 1, so n minus 1 here is the last element, right? The last element. So if index equals graph the last element, that means we reached it. So then we could add the last element to the path, right? We'll add that index to the path, and I'm going to use a copy function. So we're going to do result dot append path.copy. And the reason why I'm doing copy is because of the recursion. It's not going to keep the path variable. I think. I could be more sure of that, but this is, I think, more guaranteed anyway. So we're going to do that. Otherwise, we're going to loop through all of the elements that index has, like all of the neighbors from that index. So for vertex or node, let's do vertex. Vertex in graph of index, right? Because we're looping through the elements for that vector, vertex. Let's do node. For that node, we're looking for all the neighbors in that node. For each neighbor, we're gonna it's interesting. For each neighbor, by the way, the starting path is always going to start with well, not 0, but actually, would it be 0? We're always starting at 0, it looks like. But first, just to be sure. So we're starting at the 0th index, and this is our current path with 0. So this is assuming that 0 is going to be our starting path always. Otherwise, we would need to say, okay, graph 0. But that doesn't make sense because it shows our index. So it's guaranteed to be 0 in this case. So for each node in 0, we're going to add that to the path. So we're going to do path.append node, right? Because if we loop through 4, 3, 1 here, it's like we want to add 4 to the path, right? So we add 4 to the path, and then we want to jump to this part, okay? So we're going to say DFS of node, and we're going to push in the path also, like pass in the path. So what's going to happen here in the first iteration? We're going to start at 0, right? We're pushing 0 with this path because we always see itself first. And then we're going to then go through all of this neighbors. So we start at 4. So we add 4, so it's 0, 4 now, right? And then we go into 4. So go into this, but it's blank. So we go into it, and index, which is 4, it equals graph, the last element. Actually, would that be right? If index equals graph minus 1, what's graph minus 1? Well, that would be 4, wouldn't it? Would that be a number? How do we know we reached the last 0? I think that's fine. Yeah, this would be 4, I believe. So if this matches, then we would append 4 again. That doesn't seem right. Since we added it, I think we're just gonna pass over the path copy, and we're gonna return res. So let's see how we did so far. So we created a function DFS. We passed an index 0 with the initial path of 0. If graph -1 is going to be the last index number, right? Because it's a list of lists, I believe. That should be right for graph. That's not true though, right? Because how about this? Target. I'm gonna set target to length of graph -1. Okay, so we'll just pass in target here because I think I was incorrect. It's gonna given the list there. So we're gonna have our target graph -1 if index equals the target. So this 4 equals 4, then we're gonna just copy over the path to the result list, and then that's it, right? Because we append every node anyway for node in that node, for all the neighbors in that node, and we're passing in the node path and target. So I think that should be right. Let's give it a shot. that wasn't right. Okay, I think I see what I did here. So we see 0, 1, 3 and 0, 2, 3. I added 0, 1, 3 also. That means like I just didn't pop. So this is where, I forgot, but we need to backtrack here every single time, because when we go from 0 from here, right, we added 0, 4. After that, we want to pop off 4. We want to do 0, 3. Pop that off, then do 0, 1, so that we can see all the unique paths. So how do we do that? We're just gonna DFS. Sorry, we're gonna pop whatever is at the end there. So once we finish our iteration, we're gonna come back here. So we're gonna pop off what we first saw from the first node. Pop off that first neighbor. So if we do that, boom, got that, boom. Okay. So this was this was cool. I think one thing is, if you didn't have a DAG, then you would want a set that would say that, okay, we visit. So you would check on membership, right? Like, oh, did we visit this node or not, or something like that. But in this case, we don't need to worry about that. But yeah,